All right, good evening, everyone. Before we begin today's session, could you please type in the chat box if I am audible? Okay, great. Thank you, Somil. All right. So, without further ado, once again, good evening, everyone, and thank you for logging into the battery modeling session today by Yashwanth and Sreenivasa from Ather Energy. So, the purpose of today's the purpose of today's session is to stimulate thought-provoking discussions amongst engineers involved in developing the battery system. There will be the following topics that shall be covered: an external perspective, where you model the context or the environment of the system; an interaction perspective, where you model the interactions between the system and its environment, or between the components of the system; a structural perspective, where you model the organization of a system or the structure of the data that is processed by the system; and a behavioral perspective, where you model the dynamic behavior of the system and how it responds to the events. So, a bit about our speakers today. Yashwanth has had more than 10 years of experience in system engineering, controls, software engineering, and he has worked with big names such as General Electric and Honeywell. At Ather, he is responsible for system modeling and simulation. He also holds an engineering degree in electronics and communications and a diploma in embedded system CDAC. Srinivas comes with more than 6 years of experience in the field of power electronics and control systems. He joined Ather in 2019 and takes care of the system engineering. His prior work experience includes roles at Think Cloud Technologies and Quest Global, and he has a master's degree in power electronics. Today's session is being sponsored by Ather Energy, which has built India's first intelligent electric scooter. The company manufactures two scooter models at present, which is the 450 and 450X, and they also have an established electric vehicle charging network called Ather Energy. So please do allow me to welcome both Yashwanth and Sreenivasa to take the podium today. Yashwanth, please go ahead.
Thanks. Hi, everyone. This is Yashwanth, and I have Sreenivas with me, who works in system modeling and simulation at Ather. I'm going to share my screen right now, and just let me know if you guys can see it. You guys can see it, right?
Yes.
Okay, all right. Once again, welcome to everyone. Today we will, as discussed by Kathy, we will we'll talk about and we'll discuss on system modeling and simulation, and a little more deeper into battery. And first we will set some context to this whole discussion, and then we will go into details of the system modeling and the sub details, like battery modeling and various other components. So warm welcome to you all, and let's get started. We'll take a Q&A at the end, probably for 10-15 minutes. And meanwhile, if you have any questions, there's a Google link to put up your questions. Feel free to add in all your questions there. And let's get started with this. So to begin with, let's just know a little about Ather. Most of you might have been already aware of this, but let's just see a little background on Ather Energy. So it was founded in 2013 from IIT Madras alumni, namely Swapnil and Tarun. It has so far received more than 100 million of funding from various big companies like Hero MotoCorp, Tata, Tiger Global, Sachin and Bini Bansal from Flipkart. And it has a presence in more than 10 plus cities right now, and with the total employee strength of 750 plus. And we are, as you all know, the portfolio is of fast, intelligent, and electric scooters. And not just the electric scooters, we are into building the EV infrastructure network as well. So to our technical feathers in the hat, we have 44 patents in India, 5 international patents filed, 111 design registrations, 3 international design patents, and 100 plus Indian trademarks. So this is a little bit brief on the company's background, and we'll go further. So basically, what do we do at Ather, right? Most of you might already know, and those who didn't know till today, probably most of you would have watched India versus Australia match today, where you could have seen some ads today. Hopefully, you like them. And so we have been into design and development of these electric vehicles from scratch in India. This has been like pioneering effort, not just to build the electric vehicles, but also to set a gold standard in the industry, right? That's what this company is known for. The electric vehicles are designed and built from scratch here, and as we know, we are kind of changing the image of electric vehicles and driving the adaptability in India, and changing the perspectives with which the electric vehicles were looked upon, before and after Ether. And every It's not just that, every component, single component that goes into the vehicle has been customized and fit for the need, and it's been like engineered for the purpose, not just to have any component on it, just for the purpose of it. And all this revolves around our customers anyway. So customers centric design is what we believe in, and hassle-free ownership is one of the buzzwords that Ather is known for. Right from ownership to post service, post purchase services, and everything. So this is like a total bringing a new perspective of adopting electric vehicles in India. This is what is Ather all about. Going a little forward, we have right now in our portfolio, as you could see, 450 and 450X. No rewards for guessing the other colors that you might have already seen on the roads, especially those who have been in Bangalore. You would have seen some test rides and things like that. So these are the two models right now, and a little bit on the spec. Being electric comes with added advantages, like we have the fastest acceleration in the segment, and beyond. Probably we have like 0 to 40 in 3.3 seconds, which itself is a benchmark in the industry. And the top speed is easily 80 kmph, and much beyond that. And connectivity, we have a 4G connectivity, 85 kilometers plus is the true range. 7-inch dashboard. Yeah, it comes with Bluetooth connectivity. Projected range under IDC conditions is 116 kilometers. We have onboard navigation, over-the-air updates, gradability to much higher level, and park assistance, reverse mode, and a lot of things which comes along, which are not seen here. You should probably try this out at your nearest experience centers probably. Going forward, so what we'll do here today is we will anyway talk about battery modeling, but just to set context, let's not jump into the battery modeling right away. I just wanted to take it a step-by-step sequence. We will talk about a little bit on system modeling. Why do we do modeling? A brief intro on the modeling and all that. And why do we do modeling? What are the advantages that come with it? And what is different perspectives of building up a model? What are the components to it, and different approaches, and finally some small takeaways from this whole session. This is what I'm expecting from this whole session. Yeah, let's move ahead. Kathy, I'll just keep repeating this once in a while because I just want to make sure I'm being heard all the time I'm speaking.
No
I'm audible, right?
Yes.
All right. Okay. Okay. I need this feedback once in a while because this is important for me. All right. Yeah. So let's just begin into why do we do system modeling, right? Let's dig little probe on the surface of it first of all, like why do we need to do this? Why is system modeling important, right? So whenever you're building a complex system, or a particular system, it's very, at a first hand, it's very difficult to get an overall perspective of the entire, system, which is under consideration. It's really, you can't visualize the entirety of the design and development at one stretch. So what does model do is, a model represents an abstract form of a system which we want to study, right? It's easier for us to study any system if we have a perspective of what the system is about. What are we expecting out of this? What is this system expected to behave in certain particular conditions, and things like this. These are like top level things that would come to our mind when we get started with anything, not just a system, not engineering, anything, right? We would want to have an understanding of the system. What system modeling or a modeling in general provides is that particular understanding, how we go about designing that particular system. And it also helps to maintain all the information about the entity that is being represented, and we will talk about that in further sometime later. Why do we do modeling, right? One of the things that we keep probing at, why do we do all this, right? When, as I said, when we are building complex systems, if be it electric vehicle, be it locomotives, metros, or complex systems like commercial aircrafts, or defense aircrafts, or anything, anything that is complex for enough for us to think of a system. We can't imagine the whole system in its entirety. We want to, modeling exactly helps us here. It helps us to visualize a system as it is, or as how we want it to be. This overall perspective of what the system is about is, can be understood by modeling. It also helps us to give a structure and understand the behavior of the system. Also, what it does is it gives us a template, and it helps us to guide in building the system, right? We'll talk about that in a while. How would we approach that and all these things. And also, modeling kind of gives us a documentation. For those who don't believe in documentation, it also helps in giving us some kind of clarity on what we are building in terms of documentation as well. And we will see that we have plenty of examples across aviation and many other platforms where documentation is one of the critical evidence that you produce as part of your engineering design. Where do we use this modeling, right? Do we say that, do we just use this modeling only at the initial phase, or during the engineering phase, or POC phase, or after that? And where would we exactly use this modeling? To me, as my experience goes across industries and different phases, to me, I firmly believe that the modeling and simulation is applicable for entire life cycle of the product. It's not just at the beginning or during or after the a system is built or a project is done, but it's across all the phases. In the requirements phase, which is typically called requirement engineering process, it helps us to define what we want to build about the system, or like how to define requirements for a system. Be it different approaches, like SysML, UML, other things, but it also helps us to visualize the requirements, how the so in a complex systems, right, when we are trying to build, each system has subsystems, and subsystems interact with each other, and each has their own set of requirements. How do we manage the requirements? Everything can be kind of brought into modeling perspective. Modeling in the sense, I'll come to that a little while later. Okay. So implementation, right? So of course, when we are doing implementation, we would want to try few approaches. We would want to stick to one. We like few approaches. We might further probe them and then find that they are not useful, and then we ditch that and go to a different direction. So what modeling helps us is it speeds up the implementation of the design process as well. So it is very, very critical in the implementation phase as it is in the requirements phase. Basically, it helps us to understand and execute the whole system that we want to build. And post implementation, like I said, it helps us to document the system structure and how it works and what are the takeaways or learnings from the whole things that we have been doing so far. So especially this kind of this particular approach is typically seen in aviation, where it is very critical that we produce documented evidence of not just the documents, requirement documents, which we call PSAC, different names, right? SFS, other things, functional specification and things like that. But also it is important, equally important, to produce the evidence to some certifying body that, hey, this is what we have done and this is how we have done it. And you could take a requirement, how the requirements have been flown down to lowest possible level. So that's more important in certain domains, and it has equal or more priority as other phases of the requirements, or the building system, right? And what are the approaches? Which type of approach should we follow? Right? There is no particular hard and fast rule as to what type of tools do we use and what is the approach that we take. These depend perspective to depending on the system to system, industry to industry, and a lot of things. For example, right? You have you could basically, the whole modeling approach can be done for things as simple as, like, ticketing system in an aviation industry, or it could be a banking system, or anything. It just need not be in engineering domain. Any system which has some interactions, and where you give certain input and you expect certain output, you can represent it in as a system, right? Bluntly put, or at least on paper. So there are different tools and methodologies available. You could probably go through them in detail. We'll not touch upon a lot of them, but yeah, simply put, there are a lot of when it comes to modeling, typically what we think is that we have to use certain tools, certain code generation, and certain approach and things like that, right? So it's not just that. We could there are some tools called UML, Unified Modeling Language, SysML, System Modeling Language, and a lot of things, where you could define a logical flow of things as well, where you could define how in a aviation, or in any other industry, or banking industry, anywhere, you could represent how a different entity interacts with another entity, right? So these are some advantages and of using UML and other things. So, and which is particularly of not our interest today. We will focus on mathematical modeling, and there is no one particular tool. We have a number of tools available in the market. We could choose any of them as per our convenience. And this is basically for engineering purposes and other detailed analysis that we could use. So far, this is what we would discuss, and we'll move forward. Kathy, I'm still audible, right?
Yes, 100%.
All right. Okay. Yeah. Thank you. Okay. Moving on. So we just discussed why we would do modeling and what are the advantages, right? So conventional, typical engineering, methodology is, you define a set of requirements. You first want to understand what you want to build, and then you come up with some set of requirements. You build a proto again, and then you do some validations, verification, and then you find out something is not working. You go back again, rebuild the system. So this kind of loop continues, right? So this is the conventional method. Where you have requirements, you build prototype, you do some data collection, analyze the system, and then rework or no rework. Finally, you do rework based on the feedback that is available to you, based on the test data. You conclude which is working, what is working for you. So typically, this is the simplest approach we would want to take, with no other overheads and all that. But what it comes with, this approach comes with is, it's first of all expensive. That meaning anything that goes wrong, of course, you have to do and re-engineer a lot of things as a prototype, and then you retest it and again, which could be time consuming and expensive. So that's what that's where the model based methodology comes in, where you have some set of requirements. You do MBD, let us say MBD. What we will do, we'll figure out later, and build some models, simulate it, understand your system better and better. You do some basic tests, not that you can completely skip the test part of it. You do some tests, validate your model, validate your engineering design, and then you build the final prototype later on. So what it helps is, whenever there is something which doesn't work, you get enough time and enough, in a least expensive way, you could actually refine your engineering decisions. So it is time efficient, very fast, because we are not building the system per se, but we are building a proto of it. We could go as close as possible or as superficial as we want. So it depends on our application, and our budget and other constraints as well, and to what level we want to do the modeling, and analyze the performance and plan, and do the design phase and everything as per our plan. So this is what basically we want to do as and when we want to do a model, introduce a modeling approach to this engineering, conventional engineering method. So this is what typically we would like to do going forward. So as I said, right, you could have a different approach. Either you could build the proto, test it, do some tests, get some data, analyze, done, right? And parallelly, so this is what you're seeing here. You have a physical system. You build a physical, system, and then do some experiments on it and try test it. Basically, validate your system that against your set of requirements. Get some data, and then once you see that it meets your hypothesis or your objective, you say it is done. Parallelly, there is something where mathematical models could be built for the same system, both represent the same system, and you could do some simulations. You get data out of that, and you could compare it with what actually your objective is, and also with experimental data, and then you can go ahead building your own system. So this is what typically it would look like. Some scientific, some extended scientific methodology and all that. So, but typically this is what we do. It doesn't, mind you, it doesn't bypass what you actually do on the vehicle or a system. It would help us as a parallel objective where you could spend or save a lot of spend energy meaningfully. Basically, this is what the modeling approach enables you to do. Yeah, so when we start to model, right, a lot of things would come to our mind. Hey, I don't know the system. What would it look like? How do I model? What do I model? There are so many things. There are so many uncertainties. A lot of things, right? So basically, these are some questions I could think of that came to my mind. Say, which model is used to describe a certain aspect of the system, whether that particular aspect of a system that we want to think, can I be able to model that? Would I end up spending a lot of time on that, or would it be easy? A lot of things we wouldn't know when we are about to start something, right? And are there some overlapping areas? Would I be, like I said, redundant? Would I be building this model redundant, or it would be serve my purpose? It would not. So a lot of things like that, right? Same kind of information, different model. So yeah, there would be some duplication. Say I'm building a vehicle, right? For all of you are working for building some vehicles for your college or for your passion or anything like that. So we would build up something where we could have done differently, and we could have overlapping logic in some places and things like that. So all this is very much certain when we are doing things for the first time. So describe the model, all relevant aspects of the system. So does my model represent the actual system that I want to build, or a subsystem that I want to build? This is one more challenge where something that would not be clear as and when we are doing something from the beginning, right? Which information is used within the model? What do I use basically inside the model? What do I use? And how are the models linked to each other? How would I make models talk to each other? I can build some model, and if it is like left all alone, it wouldn't serve the purpose. It has to talk to some subsystem, or it has to interact with some UI, or it has to give some inputs. Given some inputs, it has to give me some results. So that is what do I expect out of each model that I build? And typically you can probe further a lot of questions, whether do I have the big picture of the whole system? What components would I have? What are the variables in each component? What would be a constant? Say, for example, if I want to build some battery or some particular component, what are the constants? What wouldn't change? based on my environmental conditions, what would change? So it's not very easy to figure out in one go. It takes some detailed understanding of the system, any system that we want to build, right? And what are the variables in each component? So first of all, how do we understand what are the components inside it? How many state variable does each component has? So a lot of things, right? A system and its component is really a complex thing. And of course, the next step is identifying the interfaces, right? So what parts would I need to test? Would I test the entire thing? Would I test some part of it? Testing some part of it, would it help me to understand that entire system is working fine? Would I be spending too much energy on testing everything? A lot of things, right? So how much test data I would need? A lot of things is certainly not known at the very beginning. Eventually it is something that we would figure out as and when we are doing something. And so yeah, of course there are a lot of questions we can keep going. Basically these are some questions that will come to our mind when we start off thinking, doing some model. So basically, let us, for all our common objective, let us consider we want to build a vehicle. We can call it a two-wheeler, three-wheeler, four-wheeler, whatever. So what typically it would have is a vehicle. Say in that environment, say we have this in a particular environment where we have, it has to give some, it has to take some, any system, right? It has to, it can't be a black box or not react to an environmental condition, right? Or some inputs. It has to, the whole purpose of building a system is it has to take some inputs and give me some output, right? And which we want to analyze for engineering purpose. So this is what a typical vehicle model, if we take, would look like probably. Driver is a typical input provider to the system. Let's call this vehicle as a system. And based on your ride and the vehicle would give you some feedback, which a driver analyzes, some physical, some in other means, and he would react to those inputs and again give the output, meaning which is again input to the vehicle and all that. So this is kind of loop that we would see. And a drive cycle is what a driver would expect, right? I would want to operate my vehicle in a certain condition, constant speed, or a particular track of or a particular IDC, Indian drive cycle, a lot of things like this. So typically let us assume this is our environment that we want to operate in or we want to discuss further. uh, so how would we break these things down? Okay. uh, First we would want to identify, like we have identified in earlier slide, we have a driver who would provide inputs and a vehicle which would take an input, and there's some close loop and some kind of interaction between those two. We would first identify and break down the system into functionalities, functional subsystems basically, right? It is very easy for us to identify in this particular case things which are very familiar. For things which are not familiar, say we have a project of some defense system which we want to analyze, it is, or anything of that sort, it would not be very easy to functionally categorize the subsystem. So there is a lot of exercise that goes behind it to understand what are the functional subsystems, meaning what are the specific functions that this would do, and how would I categorize my systems into subsystems, whether I would break them down into functional or or any other different way. So identify the functions that come up with the so first of all we would do some identify what are the subsystems that it is composed of, and then identify the boundary diagrams. Okay, say for example we have come up with in the earlier picture some four-wheeler, for example, or two-wheeler. So what are the functions that I expect out of that? There would be some battery, there would be some motor, or there would be some other electronic devices, a particular dashboard in some cases, and things like that. So what would be the function of each of these subsystems? We would identify and draw a boundary diagram for each subsystem, meaning what this a boundary diagram is, how this particular subsystem, when we break that into a finer component level with the details, how would this subsystem interact with other subsystems? What are the boundaries of each system? Meaning where am I putting some functional requirement into, right? Where would I expect some core function to happen? That's all. To identify the specific inputs and outputs for each subsystem. So the first step is break down your system into sub-functional systems, and then we would identify what are the inputs and outputs from each of these, right? Typically, that is what we would analyze system to behave. identify the producers and consumers for each measurable quantity. So we would, for once we have identified a system, we would want to know what are the measurable quantities, right? Say for example, you have some torque, you have some current, you have voltage from each system that behaves differently from system to system, and there are some downstream systems, there are some upstream systems, and all that. So who are the producers, who are the consumers? This is something typically we can identify. And how do we want to go about modeling each of these subsystem? Again, this is totally based on our need. We might choose to go, for example, in this vehicle, we might want to go a very detailed modeling in terms of in case of a battery system, and we could probably touch upon very minimally on the motor or any other subsystem. Say basically we would decide how would what I want to convey here is there is no particular criteria to model a particular system or subsystem. You could go design a system in a very fairly simple way, because you have some inputs, you have some output, and in between whatever logic you would want to write, it would be very fairly very simple, or it could be as detailed as you would want to do it, right? So it's basically totally based on our need. We could go as detailed as superficial as we would want to know, but provided that it gives some expected outputs and it takes some certain inputs. So for example, let us break this down. Say for example, for our ease, let us say we were working on some electric two-wheeler, and we would want to break that subsystem into different subsystems. I'm not saying these are the four systems that we are bounded to to break that system into, but these are typically what we can break down the system into. We have some battery management, which consists of again BMS and battery components, and we have a powertrain, we have a motor, transmission, wheels. We could break this down into typical functional subsystems, as I said, and see how to go about each of these. This is what probably we'll explore a little more in BMS side, and probably touch upon other subsystems. Okay, so we have, we'll get started with the battery. Say we have BMS. You all know, we've been working with probably all electric vehicles by now. So we have a battery which consists of all lithium-ion cells packaged into a lump called a battery. Consists of PCM and other subsystems and other components internally, a lot of bus bars, a lot of interconnections between each cells and all that. Like I said, just the battery, we could go a lot deeper, or like we can do some very simple mathematical modeling for the battery and the further components, which are cells, of course. So we have some BMS where you could monitor the performance of the battery by getting some feedback from the batteries, typically monitoring the voltage, temperatures, currents, everything on the battery side, on the battery. And it also, we could also control the charge and discharge and cell balancing, and a number of things we could do on the battery with the help of BMS. Yeah. So what are the typical limitations when we go about battery modeling, right? We would just glance through them just to begin with. Kete, I'm still audible, right? I'm not talking to myself.
No,
Hello?
but I was. Yes, you're audible.
All right. Okay. Sorry to keep you, in the loop. Yeah. Okay. First, we'll see. Yeah, thank you. We'll see some limitations, right? What are the cost and time aspects of this whole modeling? So as I said, calculation of model parameters is based on the actual measurement. So anyway, battery modeling is not something that you take a spec and you could do some come up with some battery. It involves some cost and time, and it also needs some actual testing and measurement, and you have to build some confidence by doing some tests and all that. So a lot of cost and time criteria is involved, and a lack of generality. This is one of the key things. Because you could pick up a cell or do a lot of tests, come up with some characterization of the battery, and still find that it is not actually something which is not helping you, or it is not actually meeting your understanding. So that's where one device would not represent another device, right? So there would be some manufacturer to manufacturer variations, and there could be cell to cell variations. A lot of uncertainties are still involved, but we would want to generalize what we want to study. That's the whole purpose of this battery modeling, right? That's that's the objective actually. So validation is carried out on the battery under specific battery under measurement. So what I want to convey here is, you could do pick up a cell, any manufacturer, do some series of tests, and then come up with some understanding based on our tests and simulation, and then see that when you put it across a different cell or a different make, your physics or your logic would be the same, but again you would have to do a lot of fine tuning. So that's been this. This is one of the key things that we would observe as and when we are modeling the battery. So what is the solution for this, right? So to begin with, uh, we would always have some data sheets from from the manufacturer, right? So always we would rely on the data sheets, resort to the information available in the data sheets provided by the manufacturer. Of course, this is what we do basically. And what the key thing here is, variable accuracy model template, meaning any manufacturer, right, he would not be giving you any spec, any characterization or any information to the spec, to the dot, right? He would say, even for the capacity of the cell, he would give you typically some range, and he would give you some boundary conditions. He would give you some boundary conditions where he would say, this is the range that you would want to operate this particular cell, right? So usually the spec contains some boundary conditions. First, it is very important for us to understand the boundary conditions within which we understand the cell or the battery that is under consideration, right? So what comes in the data sheets typically would have some range. That is what we want to understand from this, and we will have to work around that's the key thing. Okay, so how I try to put some flow to it. Let's see how this flow works. So you have some battery sheets, you understand some data sheets. You would, as a designer, you understand, let's assume we all understand these data sheets, and you start some series of tests. Okay, first we will see what typically what can we do about it and all that. But it is important for us to do certain tests and extract the data out of these cells that we have, right? um, I'll keep talking about cells because as an further I would assume that as a battery we would break down things to cell level, and then first understand the cells properly and then build up the battery level model at a next step. This is how typically we would go about it. Okay. Because you might actually that's what I said in the beginning. Like, if you really want to understand the battery as such, I don't want to. It depends all again on your needs. You could say that I don't want to, like, characterize myself. I'll have picked up a battery for my purpose. I will understand the battery at a battery level very well. That's very good actually. We could do that as well. We don't need to study or at a cell level or differences and a lot of things. So we could do take a battery as a subsystem and we could study. But if you want to further probe it down into further subsystems, let us understand a cell properly, and then probably come top down, bottoms up, as and the as per the subsystem design that we would want to do. So we have some test data. We understand the batteries well and populate a lot of data. There is no end to how much tests that you could do, how much information that you could get out of it. You could very well dig as deeper as you would want. So, but typically, limited set of data is enough for us to understand about the cell. And parallelly, let us say we have built a model and we will have populated the data, and we would do some correlation. We have data from the cell testing, and we have data from the model. We would like to correlate and also do the same kind of comparison with the actual measurement and see how well our simulation and the measurements on the actual cell would look like. We will see this, how this goes. What I want to, the key takeaway from this slide is that it's not just the model that would be helpful for us to understand a battery. Typically, model and the test data would go hand in hand. Let's not say that at the beginning we said, hey, modeling would do everything, modeling is great and all that. But typically, when we are building something, right, we would want to build the system as per spec. So we would always want to close loop with what we have from the simulation and what we have from the measurement, so that whatever model we have at hand is accurate enough for us to believe and trust next time when we use it for some other purpose or for a different objective. So we can't avoid measure physical testing and measurements at all when we are actually building the model. So this is the point that I want to convey here. So, right, as I said in the previous slide, there is a lot of things that you could build with to begin with, and you could build on into a battery model itself. It could take a complete session or even multiple sessions if you want to dig deeper into this battery thing. So let us understand what we want to do out of this battery modeling, right? Uh, as you all know, all of us are users of cell phones and laptops and computers and all that. We all kind of are used to lithium ion cells, so it has effects on. It's not like it is it, what do I use, it's not unreactive to external environments. It has the cell has of certain functions, and it reacts to environment subject, and when it is subjected to certain way. So it is the way as lithium ion cells would work varies across different functions, like the usage, usage in the sense charge discharge cycles, the temperature effects, you have capacity effects, age, capacity in the sense aging, and a lot of things like this. So this is what we understand about that, right? So let us see that how do we go about this whole modeling aspect. For example, we could take a cell or a battery pack and say subject it to some runtime, like say subject it to charge and discharge, and then we understand certain things out of it. As simple as a charge and discharge test would give us some information about the battery, and then it would also we could also infer something about the SOC. And if we say we can also find something about the SOC OCV relationship, right? And again, this SOC, we could do some transient response analysis or a steady state analysis. A lot of things we could do. It all depends on how much we want to understand about the battery. So for our purposes, say if we want to for example, if you would say I will stick to some battery, I will only work on that. I'm not going to change my battery pack for or the same make for the next 5 years or something like that, or I only want to understand this battery pack. I don't care about the generality of the model of the battery pack, right? So in that case, there are certain limited elements of the battery that you would understand and keep, and also I would use it for a certain time, and then after that I'm not going to use it. Every time after say 1 year, I'm going to replace my battery. Is something that is of your, if that is how we understand certain usage or application. We might not want to go into the aging effects and all that. And also, if we want to know about the climatic or temperature effects on the battery, we would also very well understand only in that particular range, because lithium ion cells or any particular battery has a very different behavior at say lower temperatures and very high temperatures. So if we want say a particular sticking to particular certain range, we would as well say that, hey, I want to understand the battery only in this particular range. So a lot of things depend. I'm not saying this because there is a lot to study about and understand about the battery. It all depends on our application. So that's why I'm saying whatever is our application, we would want to study only that. But if we want to dig deeper, we would explore a lot of things. So that comes to second order effects, which I try to say that how is the battery voltage will be affected based on the temperature, how it affects the capacity, how temperature affects the capacity, how both the things affect the capacity fading due to cycling, due to storage, a lot of factors. So it depends on the levels that we want to understand, right? Say for example, if I've mentioned here at level 1, we could say I will just do some basic tests for understand about the battery, and I'm happy with that. Or if I'm okay, do some steady state response, and next step would be probably transient response. Say the subject, how would I want to understand the battery when it is subject to extreme conditions, say a drive cycle at different temperatures at different age, a lot of things, right? So 5 years down the line, I would want to know how my battery would behave at different temperatures, a lot of things. So it all depends on what we want, and we minimize our testing to only that particular zone or field of application. So this is what I want to convey here, meaning there is a lot of things, a lot of depth to which you could go in the battery modeling. But if we clearly know our boundary of application, we could minimize a lot of energy and concentrate only on specific application that we are looking at. Okay. Yeah. So as I said, right, take the battery. or the cell, subject it to a charge and discharge cycle, you get some curve. This is good enough for us to understand a lot of characteristics about the SOC. The red line is a discharge curve and blue is a charge curve. So so typically you would understand that 0 to 100 SOC, you have some on the axis you have a voltage. So you always know 4.2, 4.3 is the top voltage, and basically you believe you could understand by now that the it's not like a charge and the discharge cycles are all unique. They are all so they are all same. They are all unique, and not just this particular so just with this data you could understand, dig deeper into a lot of things about the battery modeling. But not just this. For example, this particular curve that you are seeing on the left side, this could also change based on the amount of current that is subjected to, right? So what is the C rating of the or the capacity that you would, or the current that you are as studying it with, right? You would want, if you see the right side curve, you would see that even with different charge or discharge profiles, this or the discharge capacity, you have with the different discharge rates, you have different voltage behavior. As and when you increase the voltage current or the discharge currents, you also see that the voltage also drops down. On the left side at T0 or the capacity 0, you could see it's not from the same point that all these originate from. You have different voltages based on your operating conditions. So again, specifically, you have to understand what is your application, what is the maximum current you are going to subject it to, either charging or discharge. All these boundary conditions is very important when you want to study. You can't keep studying or understand about the battery right from 25 amps to 500 amps. Right? You could do that, but it again depends on how much energy we want to spend on it. Yeah. So yeah, like I said, you have a cell has a a charge capacity, and you have on x-axis you have charging time, and you have different plots on the x-axis, y-axis on the left side and right side of the curve. Kete, I'm audible, right?
Yes. Yes, you are.
Okay. Yeah. Sorry. Okay. So yeah, based on your constant current and constant charge cycle, again your voltage varies. You would have some different curve based on your charge currents and discharge currents, and a lot of observations you could draw from the curve as and when you are testing. Um, so this typically is an example that just I want to make it clear that particular constant currents and different current profile, your voltage would change as per your characterization of the cell. Okay, that we would see further how and why. And also what we would also want to understand is your OCV versus capacity also depends on the temperature. Okay, as you could clearly see, your OCV changes, and the curve that it follows differs from different at 0 temperatures or -10, probably any temperatures based on the spec. It would vary differently based on the temperature that we want to when we want to subject it to. Okay, all this is typically different type of data that I want to show, because we would want to limit our study to certain cases based on our application. For example, we subject, how would we model the entire battery, right? We would want to understand a lot of things about battery. Uh, so say for example, if we subject this to a DC internal, if we subject this particular cell to a discharge cycle, say for example, we see this, there is a discharge curve pulse, and we would want to analyze how this cell behaves in this particular case. All good if this were only a resistive load, but typically our load, it depends again on the load that we were using this battery against. That the nature of the pulse or the response from the cell would be slightly different from what we would expect. So there would be some RC characteristic which, along with the ohmic component, we would see some non typical response of this RC, which we would want to study. Okay, for example, even in charge or discharge, there would be some RC component that we would want to understand. So how do we go about modeling, right? Say, for example, you take some cell and subject it to a charge discharge cycle. You have some instantaneous response, which you could actually represent it with R naught. Say some that's what I meant by DCIR, DC internal resistance. Each cell has a different internal resistance, and based on that, you get a response of it. But not just the instantaneous response, but there is some delayed response where you could actually see in the previous or in this curve as well. Again, here represented by the below graph in the green, right? So there is always this delayed response, which is called tau, which again depends on RC. How would you want to model your or analyze your response? Say, and again, the blue one is the open circuit voltage, which is represented by the EM in the curve again above, in the diagram above. So this is typically how your response would look like, right? And you know the reasons why each of these is represented in different colors, and what contributes to basically that kind of response. So this probably what I want to convey here is, it's not just the DC internal resistance. You would always you also want to, based on your test, right, you would also want to characterize the nature of the delayed response and other factors more clearly. So you would want to have some R1 C1 and R2 C2 and so on. You could, based on the level of accuracy that you would need, you could extend this further, but typically what based on some studies or our analysis, our experience and analysis, it's typically we could say that a second order is what we probably would need to go to perfectly or almost accurately represent the system. So typically we would say R0, R1, C1 and R2, C2 is typically what we would need, especially at different SOCs when we talk about, right, at very low SOCs, the nature of the whole response, the voltage response would differ from how it is at a different SOC. So especially if you want at lower SOCs and very high with very high accuracy, you would want to represent your system with more and more details. So, but how do we go about? So this is what is represented here. It's all like it's the same thing again, and each of these again is a function of SOC and temperature. So it's not just each of these R and C here again is a function of SOC and temperature. So we would want to do a lot of tests to understand the nature of how these R0, R1, C1, R2, C2 behaves with respect to different environmental conditions or different changes that we subjected to. Okay. So to clearly understand this behavior, right, we would want to do some series of tests on it. Basic, like we have seen earlier, like a basic charge and discharge also could give you some understanding of what is the operating voltage, what is the OCV versus SOC relationship and all that. But and again, if you want to dig deeper, we would do something called a HPPC test, which again would depend on the percentage of it would give us some idea about the SOC at different SOCs. Again, say for example, you take a brand new cell, assume that it is fully charged and the SOC is 100%, and you subject it to a charge and discharge cycle. You have some response on the HPPC test. Okay, and typically the same HPPC test, you repeat it on the same cell at a different SOC, you would slightly get a different nature of the curve, and so on and so forth. So you would so basically what the takeaway here is that the voltage response is dependent on the SOC. So you would want to understand how to characterize the R and C at different SOCs and different temperatures. Again, this whole thing is again done in a controlled environmental chamber, or probably you could have to maintain this whole thing at a particular temperature. Say for example, you don't keep temperature at constant. Again, next time when you do the same test and would want to do some correlation, you might not see that it is fitting very well, because not just the temperature or SOC, you would also want to as a particular. So you see, you don't want to take too many variables as variables in your test, right? You would want to keep as an engineer, we would want to do some analysis keeping one thing constant at a time. So, for example, we are doing this series of tests, HPPC tests, to understand how the RC characteristics depend on the SOC. We would not want to mess up around the temperatures. Which we would probably do by varying the different temperatures, subjecting the same test again to at a higher or lower temperatures. So, what I want to convey is we would want to do a series of tests before we categorize how a particular cell would behave, how a voltage response, how the cell would behave at a particular SOC at a particular temperature. A lot of detailed studies required, and all this would go into the model. Say, and also these are like, what we have talked so much about is all about the electrical characteristics, right? Again, that depends on your need. So again, there is some thermal characterization where you would want to know as a battery pack or as a cell, how that responds to subject to a drive cycle. Say, for example, you have a battery pack and you subject it to some charge and discharge. You would obviously notice that not all the cells gets heated or cooled at the uniformly. There is some based on the conduction and convection nature of the surroundings and the material used. There would definitely be some variation at a pack level, and this particular behavior could also vary based on a lot of factors from pack to pack. It could be deviation, a lot of things, right? Material that we choose and all that. So we also want to understand the thermal characterization. This could also can be modeled. So it depends again, as I repeatedly keep saying this, it depends on what you need basically. Whether I'm okay if I just do electrical characterization and then understand based on some actual tests how this thermal characterization would look like, or would I want to understand electrical, thermal, and everything about the battery, then yeah, it comes with some effort, right? So this typically, you could, if you want to understand the thermal characterization, we would again want it to, subject it to some thermal load, and then see that it reaches a steady state, and then probably subject it to some, thermal load, and then see how much when there is no temperature rise, it's a steady state. You would calculate probably first a HA, and then back calculate, do the curve fitting for the temperature rise, and then probably put those numbers back into the same equation, and then calculate the MCP. So there are different approaches. Basically, there is no hard and fast rule to analyze or to come up with some thermal characterization. You could do, you could just take it as a black box and say, hey, this is my temperature, this is how I subject it to my. If you have fixed a drive cycle or fixed set of tests, right, you could say that if this is the nature of the input, this is the nature of the output. You could very well model that as well. So again, like I said, you need not assume that you would have to dig deeper in every aspect of the battery modeling. You could superficially say, hey, I want to stay at the top of top level on the thermal characterization. Let me dig about this a bit later. So you could use a very well black box lookup table. Say if this is the how the response is input is to this thermal. This is how the output would be. This is how the temperatures would look like, or the max temperature would look like, or the min temperature, whatever is your point of interest. You could do a lot of things by experimentation. And coming out of the battery, again, like I said, we have different components, right? So again, like I said, in the earlier case, the battery, same thing applies for any subsystem, any component, right? You could do physics-based model, or you could do empirical model. Empirical model, what I mean by that is, you do some series of tests. You say that this is the input, this is how the system behaves, and this is what the output I get. So that becomes an empirical model, which is basically data-driven model. You don't know what it does, how it does, but this is the input, this is the output. So you could as well, for things which you don't want to understand for now, a bit deeper, you could live with some empirical model saying, I would live with a lookup table for this particular subsystem. But it is very important for you to understand what are the variables that you are in that particular subsystem. How would you want to model that? Are you capturing all the variables and the all the functions that it would depend on properly or not? Again, empirical is not as simple as just putting some lookup tables. You have to understand what are the assumptions that you're making, and what is the model, data driven model that you want to run behind it. For example, the motor, I want to make it an empirical model. Say you perform some tests on the motor, derive some characterization, and tune it to match the performance. You again have to tune it based on some real tests, and then have an empirical model totally on the motor. You don't need to go into the physics or anything beyond that. So you could very well say my model for motor is a data-driven model. You could say the same thing with battery. You could say the same thing with any other subsystem that you want to study. Same thing again, you have different approaches like physics-based modeling, where you would actually want to model the governing equations of the system. In terms of motor and the drive, you have some identify some specific inputs, and you have power, torque command, and you have a torque generated, and how the whole system works. You could actually as well go dig, each component by component. You could do a physics-based model, meaning the mathematical and the thermal, everything. Like I said, whatever I said for the battery, same thing applies for motor as well. You could if you choose to, you could go into the very well into the physics-based model as well. And same thing, so again, transmission, right? So you have consists of a wheel, transmission and wheel. Say, for example, you have some torque output from the mechanical output from the motor. How this converts as a power delivered to the wheel, right? So you have some series of bells and pulleys. So all these things you could model. You have n number of forums in the internet to understand. Bottom line is, what I want to convey is, all these, there are good number of tools available in the market. If you want to study at the top level, you would want to go dig deeper. There are all sorts of platforms available, tools and environments available for you to dig deeper. Or you could take them as black box and use it in your system. Or you could say, I would want to model all these bells and pulleys, how the power conversion happens. You could do that as well, everything. But you would have to do some efficient calculations and things, which based on the type of testing that you would want to do. So yeah, again the wheel system, it is powered by the wheel, and when the torque is generated based on, so what makes the wheel move, right? Like whatever is torque applied has to overcome some kind of opposing forces, whether it is frictional, it is gravitational, if you are uphill, whatever it is. So you have to overcome some backward forces or opposing forces, and whatever goes beyond that, you would start to feel the acceleration. So typically this could also be used in the model, and you could very well model a lot of things on it. You could go a lot deeper, like how would my coefficient of rolling resistance impact the vehicle range, how a lot of things, right? Every aspect that you take, it's just one line here in the wheel system, but it could, the modeling and the type of detailing that you could go in each subsystem could be to very minute level. Say for example, how would you want to analyze the impact of the CRR on the vehicle range or any other thing. So what type of, based on that, you could decide how what type of tire should I be used on the vehicle. So a lot of things you could understand, and there are methods and methodologies are available in the internet and in general studies as to how each of these could be modeled. And this is a very brief session. I would not have time and luxury to go deeper into each of these, but this is what I just wanted to cover. And so the key takeaways is, as I kept saying repeatedly, the detail and rigor of the model depends on how you want to use it. And there are different approaches available based on your application. And your modeling would go to a deep, to so much extent based on your application. And any model, right? A lot of things depend on how you manage your model. You could you can bring up a very high fidel model which could do everything, which can predict everything. But if you can't scale it or you can't manage it, it is of no use. All right, because you can't apply. You can apply only to that particular system for which you have built it. So a lot of things comes with experience. You would want, as and when you are modeling something, you would want to keep in mind, how do you scale the model, how would you manage the model, say for any change, and how compact it is, how user friendly it is. A lot of things on that. So this is typically what I wanted to present. I've already overshooted my time. We can go for questions if you have any.
Yes, not a problem, Yashwanth. Thank you for that. It was very detailed and very informative, actually. I was actually paying attention to the whole things. It was quite a learning experience for me as well. Um,
Sure.
I
Thank you.
mean, the last time I did a systems engineering course was 10 years ago. So I
Oh,
think it is a good refresher. Um,
glad,
have you,
glad that you like it.
yes, so you have
Yeah.
the list. Oh, why has it not updated for you? Just one second. I'm not, it's, are you able to see the sheet? Because I have populated the sheet. I don't know why it's not. Oh, there you go. Yes.
Yeah.
Um,
So yeah, I think Srinivas, would you
okay, great.
want to
So
take these questions?
just if you could read out the entire
Yeah,
question
no
or.
problem. Yeah,
Sure. Srinivas, you can see my screen. If you can see my screen, you could read
yeah, I
out
can
and
see. I can see. Yeah, yeah.
you may want to read
Awesome.
out the question and take the questions.
Yeah, yeah. I'll do it. So, okay. So for the first question is, I see not many companies use model-based design, or maybe not have the much of the positions open for the same. I'm making a career in this field, but is there any opportunities? So
Srinivas,
I
sorry
see
to
like,
interject. There is some. I don't know if it's Yashwant. Are you able to hear that as well? The interruption or the
Yeah.
question?
Yeah. I think it is, but I think his voice is fine.
Okay, okay,
Maybe.
fine. As long as it's not just me. Okay,
Yeah, I
great.
can. I can hear it well. Okay. Srinivas, please go ahead.
yeah, yeah. So it seems like the first question is not pure technical. So, but I will just answer it in a general way. So, like, so actually, it's not like many companies. Most of the any automotive or any product-based company which can be represented in a physical, which can be defined using a physical equation or anything, either data-driven system. It, most of the companies actually use this approach because maybe you cannot see in a very startup companies but very mature companies they definitely use this system because there are many advantages having this type of approach in the product development because they reduce most of the money expenditure they actually physically do testing under. So it's just like they can reduce the manpower and the money on the test. So they run a simulation using a tool and get the results. So the only thing you need to do is first you need to get a good confidence on your model. So it's just like the first time when you implement the model is what it takes time and the money. But once it is done very well, so you no need to look for a physical test in the outside. So you can just run a simulation in your tool and get the spec out of it. So it's actually most of the companies use it in every automotive company. Most of the companies use it even nowadays. So the second part of the question, I don't think it's the right time to speak about it. So maybe if we have time, we can discuss it at the end of the session. So
Yeah, you could take the
I'm
next
shifting to
question, Srinivas.
I'm going to the next question. So the cell parameter variations, so slightly different capacity resistances among hundreds of cells in the needed for the SOH estimation and the stressing the healthier cells more to maximize the life. How to account for this? So okay, it's just like so. What I understand from your question is like so because it's not like we use one cell in the vehicle, so we use many some hundreds of cells, either series or parallel connected to get a whatever required voltage or required ampere from the battery. So when come because even though we when we just speak about RC and all, we always talk about any one cell that we use it to derive this RC or whatever it. But when you look at some hundreds of cells, there is no guarantee like all the cells will have the same RC properties, or the same age value, or say whatever. So and also the now mentioned like SOH estimation. So state of health. So maybe different cells will degrade different at different rates over the time. So we cannot guarantee like all the cells will have same SOH after some certain period of let's say 1 year or 2 years. So it's just like so there are some technologies battery pack implementation. That's what actually we use BMS battery management system. We will take care of. So more like any so just like I can say there is one technology we call it like a cell balancing. Let's say so. Let's say we have some of 5 cells series connected. Okay, I'm not talking about any parallel connected. I'm speaking about a series connected. Let's say 5 cells we have. So if they have a certain I used 5 so series connected cells for a 1 year time. But when after 1 year, when I looked at the terminal voltage of these cells will are different, not in the difference range that we define at the zero time, 0th hour. That means very start. But after 1 year, I got like some zero point 0.5 volts difference between the cells. That means that there is a there is a some SOH or SOC, some whatever the factor, or maybe some internal resistance got there, so that I'm getting a different voltage level at the all the five, or maybe any one of the cell. So in that case, the BMS will take care of those situations, maintaining the charge levels which is at the lowest SOC level. So by using that, you won't be having different voltages in your series pack. So I'm not just saying that's how people use. It's just like there are technologies which can take care of those issues, but there is a what to say, and there is a limit also for that to take, because I cannot keep on doing that technology for a longer time. Maybe I can use for 1 more year, but eventually that pack has to be replaced for the safety purpose. So these are the technologies they've used for this. So that's why what you mentioned, like stressing the healthier cells. That's why, because once a cell start degrading, we actually eventually degrade the entire cell pack itself. We won't be still using the pack at the same level, because the cell which was degraded, which will further degrade and cause any damage to the entire pack. So that's how some technologies will take for keep account on this type of issues.
Sure.
So,
Thanks, Samuel.
okay, I'm going
You
for
can.
the third. Yeah, I'm going for
Yeah.
the third. So, how to reliably measure a battery pack current for real-time SOC estimation? On the same note, how do we go about tuning the SOC estimation algorithms? Example, like carbon filter. Yeah, okay. So, the SOC estimation, there are like the most common SOC estimation algorithm we use any Coulomb counting method, which purely depends on the ampere that your ampere the cell is either discharging or charging, but that will again depend on the current sensing system that you use. And the second one you mentioned is like some any SOC estimation algorithm. So the another people use is like some estimation technique we call Kalman filter based SOC estimations, which will account for both cell voltage and the cell current. At the same time, you need to characterize the cell properties like RC parameters, which you need to hard code in that SOC estimation algorithm. So whereas your Coulomb counting won't look for any of these things, it only looks for the current, that whether it is charging or discharging. So if it is that case, so if you purely depends on Coulomb counting base, so the current accuracy should be accuracy should be very good. So you should have very resolution in your, and there shouldn't be any offsets in your current sensing system, and the sensing system also should be as linear as possible from the zero to the max current that whatever you design that system. So that's very crucial, because if there is any non-linearity means there is some error will we could keep integrating in your Coulomb counting system also. So I personally mentioned like normally it should be as low as in the milliamps level. It should be that much accurate. That should be, so that your SOC estimation won't be that much error. And but in this Coulomb counting also there is one problem in this Coulomb counting algorithm also, which is the initial SOC value. Because so let's say if I don't know the initial SOC value, so when suppose I started a discharge cycle, so I start integrating that current, but if I don't know the initial SOC, I don't know when I will end the charging. If it is a charging, when it will discharge also. So there should be a factor which will initialize the initial SOC before any drive cycle or charging. So that is one key point that should be we should be looking in a Coulomb counting based algorithm. But whereas the Kalman filter based things, they will be keep monitoring the voltage and current. So and inside this Kalman filters, this algorithm is already taking care of that initial SOC inside itself. So this and also this Kalman filter based SOCs have less dependency on the accuracies of the current and voltage. So because you have two factors now, even there is an error in either of them, the other will automatically nullify the amount of error. It will keep indicating as it further goes. So that's how the SOC estimation algorithm nowadays people are using. Yeah. I think that will be sufficient for your third question, I guess. So I'm moving to the next question. So can you explain about warm impedance? I had it in a post, not discussed in. So I'm also not much acquainted with this parameter because I also know about this. This is just like a curve fitting things, curve fitting, where any equivalent circuit you can generate an impedance for that circuit, whether it is purely impedance or a purely or any RC based circuit. So, but it's just like that's hot even the HPPC that we do on lithium cells also, because there also we keep but in a HPPC what we do is we take the voltage drops when for a given C rate that we do, and based on that if it is a sudden jump we take it as a resistance, and if it is any exponential based either rise or fall we take it as a RC component. So that's what HPPC will does. But the Warmberg also will follow the same thing. But I think it actually follows the EIS system. I think so, where you need to get an equation for a certain frequency or whatever the C rate that you do on the cell. I think maybe I think you already aware of that EIS, that is electrochemical something impedance spectroscopy something. I think not. So I think Wambach, but most of the people will use HPPC only because that test is more like you can straight away just derive the RC parameters for any cell. But of course, it will take some time, but you can get more accurate RC. So that means you can represent the RC values at each SOC of the cell. So because maybe I'm not able, maybe I'm not able to convince you on this Warburg impedance because it's maybe in the early stage of research to use this approach for the lithium ion cells. So,
Sure.
okay,
So,
I'm moving on to the next question.
yeah.
So from where we are getting the C component in the battery? So it's there is no like we can so it's just like okay, in a vehicle level normally the general practice people use is they will be having a hard coded SOC and OCV tables in their algos. So whenever the system settles, they will take the open circuit voltage of that and they will get the SOC, which will give us the state of charge. So and C beats also I have one doubt whether you mean C here is the C rate or the capacity of the cell. Okay, I will answer both. C rate means just like a charge rate or discharge rate, but I think you asking about the capacity of the cell only. So I will
Right.
answer capacity of the cell means every manufacturer normally usually gives a range of C because it is a that means at the end cell is like a combination of electrochemical, right? So that's why I'm saying so capacity means we normally take a nominal value because every manufacturer will give the nominal value of the seed. So so that for our theoretical or modeling implementation, we always take this nominal value for the our simulations or any simulations that we do in the our modeling. But CCOM and of course, if it is in the vehicle, so we may not be knowing how actually this is keep getting. So there are some algos which will keep measuring this value because let's say so but even you can I think you also know like so we know at the 0th SOC what could be the voltage of it. So if suppose if you start a deep that means let's say you did a deep depth discharge, so you hit at the lowest value that you can reach at the lowest line. So if you start charging it and if you reach 4.2, oh, no the capacitance in RC, the cell
Yeah.
models.
No. Yeah, Srinivas, can you hear
Yeah,
me? So
yes,
he's saying in the RC, out of the HPPC test, how is that C is what he's asking, not as in capacitance. I mean, the C rate, not the C rate actually. It is the RC.
capacitance is okay
Okay.
because I
Yeah,
am
yeah.
saying this when you actually gives a look, you say C means either it is a capacity or a it's a
Yeah.
C rate only. It's not like you can
Okay.
measure. Okay, no the capacitance. Okay, so how from where we are getting this C? I think Ms. Harit Trivedi, right? Okay, I think you are well aware of the HPPC test people will do on the lithium cells, I guess. So there are some MATLAB codes you can maybe you can download from the MATLAB file exchange servers, or you can just get it from Google. So there are some scripts available to generate that means to extract these RC values if you just provide any HPPC test data to that script. So if you say like I think I explained about this in the previous question, I guess. So it's just like I think one of the slides, if you see, Ashwin, can you just open the slides and go to, there is a
Yeah.
slide you shown like there is a C rate discharge, there is a wave shape that we actually spoke about.
This one.
I think this will be sufficient. Okay, if you look at the bottom curve, there is just like the initially the voltage is higher. There is a sudden dip. There is a happened. There is something V ohm, I guess. It's a ohmic drop, and there is an exponential shape happened, and again it reached a steady state, and again. So if you see here, the sudden drop is purely we can call it as a resistance drop. 1 second, guys. Yeah, sorry, guys. So the V ohm, if you see here, it's a ohmic drop. That means if this is any DC network, if there is a resistance, let's say in the above circuit itself, there is a R0. So if you take any current, that let's say I, there is a sudden drop happens because of the R0 drop, which is I into R0. So you can calculate the DC resistance by using the sudden jump, sudden fall in the voltage. But there is the next section of that wave, it's exponential. So you cannot simply use a I R drop there to calculate the resistance. So because that's purely because of the RC nature. That means whenever you pump a current to any RC network, so it will eventually reach the I into R drop. That let's say here we used R1 C1. It will eventually reach the I into R1 drop only. But because of the capacitance across it, capacitance won't let you voltage change suddenly. So it will let, so initially it keep charges to the value equals to I into R drop. So here you know the drop, that means you can using this exponential section of the equation. So you, by using the initial value and the final value, because when I say value means because you already done the HPPC test, you can get the initial and the end value of that particular exponential section. So by using the just permutation combinations of R and C value, whichever the RC value curve fit it exactly, so you can get the C values from it. So that's how even the MATLAB script also does. It will take the difference between that section and calculates the RC combination. That's how we actually we do the RC parameter extraction for that. So we're going to the next question. So since cell properties are very non-isotropic, won't a lumped capacitance model be unreliable? Will be unreliable. Also, what kind of tests can be performed to characterize the cells? Example for measuring the capacity. So, uh, thermal. Okay, let me look at the first one. Cell probably non-isotropic number capacitance. So, if I understand it correctly, I think is it related for the thermal behavior of the pack? If it is so, so that means lumped mass models. Actually, I'm not able to understand very well this. So I think if you are available online, you can just rephrase the question in the next slide. I will answer it at the end of the question. Yes. Okay.
Yeah, we can
So
still go to the next question.
yeah, I'm going to the next question. Yeah. So what are the worst case scenarios considered while modeling the battery model? So there isn't any worst case in the modeling because always we model the any system in the best case scenarios only. That means whichever the modeling, whether it is a physics based modeling or empirical based modeling, we always take the best governing equations or the best set of data to model this system. So the worst case scenario, if that means if I want to answer here means you should be able to use the physical equations which will govern your system very best. Or if you are using any empirical data means you will be taking whatever the possible test cases you can do on that particular system and take that data, all the inputs and output base, and that's the best way you can model any of the systems here. So that's
Sure.
yeah. I'm moving to the next question.
Yeah, I'll take one or two questions next, Srinivas. I think.
Okay. Okay.
Hmm. Can you point out some resources to study battery modeling? Yeah, you could use MathWorks website. They have pretty good detailing on the documentation on the battery modeling and simulation. There are a lot of YouTube videos, and there are some battery university websites and a lot of content actually online. You could go through a lot of papers on battery modeling. There is no one specific agenda or play repository. You could find a number of materials online. What is advised students working on electric two-wheelers? Yeah, I think the most simple and fair advice would be just having a clarity of thought. That at this point of time, if there are a lot of things that you could work on electric two-wheeler. If there are certain interests where you could want to focus on, identifying those would be the first step, and then developing some core competency in the area of your Srinivas, you could be on mute probably for some time. Yeah. So identify your core area of interest and probably which area you would want to work in, and that would be the best thing. And develop some core expertise on the areas where you want to work would be the advice. We Next question is regarding the how do we ensure the current measurement is reliable? What kind of sensors do we use? I think you would have to is a rephrased. Okay, isn't a lump thermal analysis unreliable for a cell, or how do we find thermal parameters of a cell like heat capacity? So yeah, I think thermal heat capacity, thermal conductivity, yeah, of course, lumped thermal analysis is unreliable. Is not unreliable, I would say. It depends. Is probably you could arrive at, say, for a n number of use cases, probably you would arrive at a particular range in which your model would be giving you some good or better correlations in certain areas. Say, for example, you have analyzed your thermal analysis and you come up with some model. I'm sure, it is expected that it is not reliable, or that kind of equation that you have curve fitted or whatever approach you have taken would not be applicable for entire range spectrum of temperatures and also your application. Say, for example, you subject it to a deep, a very high discharge, like say 100 amps, 200 amps or higher, based on the capacity. You would see that your thermal, output or the thermal analysis that you would actually want to do is way off. It could depend. It depends on case to case again. So yeah, thermal lumped analysis is little reliable, but it takes a lot of time and energy to keep refining it. And at the end of the day, you would likely end up with is a range of temperatures, or where you could have very best correlation or not very best correlation. Say you would be off by say like 3-4 degrees or 2-3 degrees based on the effort that you have put on your model. So how do we ensure that current measurement is reliable? What kind of sensors to use? That again depends on your application, the type of accuracy that you're looking at the system. Probably it depends on case to case basis. Srinivas, can you
Yes.
take the
Yeah,
last
yeah.
three
I'll
questions?
answer. I will answer this one. So okay. So how do we ensure that current measurement is reliable? So I think so. Everyone, all of us are well aware of us. We have wide variety of sensor system to measure the amps in a very line. So there are like shunt based one. There are like CT based things. So there are like Hall sensor based things. So but Hall and CTs, there are like maybe because they are good for to measure the currents, but the problem is here is we need the accuracy. That means accuracy and the resolution. So how much low current we can measure, that is where actually our Coulomb counting system. So that's what the previous question is about. So Coulomb counting is how we should have very good resolution, like I mentioned, in the milliamps level. So like yeah, I guess even today also people still use the sun based only for this type, because you can go as resolution go based on the sun resistance value you can use. So because they may be prone to the resistance, the temperature rise, because as temperature rises the resistance property will rise. But if you design your PCB very well, so that by keeping the sun resistance temperature in the within the range that the manufacturer specifies, you can still rely on the very sun-based resistances only. I think because I think even most of the people after the any power even in the range of kilowatt, that means kilowatts ranges also people still rely on the sun-based only because of the simplicity in those, and also you can rely on that and also the response also which is good for you even in the any short circuit protections also. So I personally suggest you still you better rely on the sun-based current measurements here. So, and also, Ashwant, I think you just answered the previous one, the lumped thermal analysis one. I just
Yeah,
want to add one more point to this. So,
sure,
because
sure,
the lumped thermal analysis model will always gives like a by assuming the entire cells into a single source of energy, and the entire thermal design that you done is surrounded that single cell, and when you do any charge discharges the heat just spread uniformly to all the surroundings. But under practical design there is no single cell because we have number of cells stacked together whether as adjacent to each other. So because of that practical design, so you cannot provide the same that means thermal path for all the cells, like say the edge cells will get to the environment very fast, that means very near to the environment compared to the cell in the middle. So the lump thermal design will give you the like a so like if suppose I have some 100 cells together and run a constant some 100 amps discharge, let's say. So the lumped thermal analysis will give you the what could be the temperature, like the cell which will be nearer to the environment, like say the edge cell only. So the lumped thermal design won't give you the temperature measurement to the hottest cell. Let's say the cell may be standing at the middle of the pack. So for that, you have to run a test on that pack and decide what is the temperature of that. That's why even nowadays, any of the battery pack system, they still use the temperature sensors instead of not using any some equations. They still use a thermal sensors near to the cells, and they will be keep monitoring the temperature because they cannot rely on the just analysis purpose.
right.
And also here one more part of this also, how do we find the thermal parameters of the cell like heat capacity and all. So normally typically people will run like some tests. Let's say you run some what are some fixed C rate discharge run and let the temperature so let's say you start measuring some locations on your let's say you put some thermocouples whichever the locations that you feel like these may cause very high temperature rise. You start measure those temperatures by running the whatever C rate discharge. So once you start logging the data, you can see the temperature variations at the different locations that you start measuring. So once the temperature reach steady state, that means there won't be any temperature rise further because system already reached it. That means system reached the steady state means the power loss in your cell is become equal. One second, guys. Sorry, it's my nephew. So excuse me for that. So it's just like so once the heat loss in the cell, whenever it will become equal to the convective loss. Okay, that means the surrounding surrounding environment will take some heat from your pack. So whenever this becomes equal, so there won't be any temperature rise in your cells. That means that is when the pack is reaching the steady state. So by once, because if you got that system, I think there is an equation in the presentation we gave. Ashwin, can you go to the presentation? I think you mentioned the equation there, the thermal equation there. Yeah, yeah, here. So if you see at the bottom, there's a Q rate equals to MCP dTd by dt and HA delta T. So if once, so here, if you see here, I think I can explain what I mentioned earlier. So here the image shown is a cross section of the cell packs. Okay, if you see here, the green cells are near to the environment. That means edge cells. So because that's why they are green. That means that lower temperature compared to the cell that is in the middle line somewhere. So you should be keep monitoring these cells which are at the middle of the pack so that you can run the thermal protection to your cells. And okay, so come to the equation. So when I say the system reaches steady state means the term MCP delta T by dt, you see that that is the thermal mass. That means that term denotes the temperature rise in the particular object. That is, let's say object here means cell. So, and the second term is HA delta T, that is the convective time. So when your system reaches steady state means the heat generated, that is that Q rate equals to the MCP delta T. There won't be any dt by dt, so that term will be cancelled out, so that there will be only HA delta T. So where the delta T means the temperature of the cell minus temperature of the ambient. So if you know the Q here, that means if you do the RC extraction to a cell, so you can calculate the Q generated, that means heat loss in the cell using the RC parameters, and you can calculate the HA parameter, that is a delta T. That means, so let's say there is a 1 watt loss happening and the system reached the steady state. So the only unknown here is HA, and the delta T means, let's say the cell reached some 50 degrees and stabilizes. So 50 minus your ambient temperature, whatever, whether it is a room temperature or whatever they want. So you can calculate the HA, which will gives you the convective heat loss here. So if you once know the HA, you can calculate the MC by using the same temperature equation and the Q value. You can calculate the MCP, which is the thermal mass of the cell, so that you can use. That's how we also do the thermal modeling in our models. So we just reverse engineer these equations to get the MCP and HA value. So I hope that will answer your question well. Yeah.
Sure.
So Ashwin, can I take that next question?
Yeah. Sreenivasa, go ahead.
So, hello, for tuning the common filter for estimating SOC, is there a way to accurately determine the sensor noise conveyance matrices that are needed, especially for voltage measurement where we use ICs? So, sensor noise covariance matrices they are needed. So I don't think there will be that much. It's just like, so okay, maybe I am not understanding what you mean here exactly. So okay, because I'm not the, because I haven't designed anyone here. So but here if you see like your, because okay, as I mentioned, the Kalman filter based SOS estimation that requires the cell voltages and the currents of the cell. So the noise correlations in the voltage estimation, I don't think you may be required that much deep level here, because the only that means the Kalman filter based SOC, the main parameters that this algo depends on is the RC values of the cell. So the how good are your RC data of the particular cell, so your SOC estimation won't be that much erroneous compared to the real value. Okay. So you can run this estimation just by running the Coulomb counting and the Kalman filters parallelly to just compare the SOC values, so that is there any error happening because of your voltage measurement system. So I don't think, because the Kalman filter based one is actually used for the true estimation of SOC. So if you run the Coulomb counted and Kalman filter based both parallelly, I think based on that you can do the trial and errors or your voltage estimation. I think you can, if that whether the voltage estimation needs to be further improved. So from that, I think you can do your trial and errors so that you can get to reach a good point of SOC estimation. I guess.
I'll see
Okay,
the
I'm
last
going.
one.
Yeah.
Yeah.
You done that
Create,
question, Ashwin? Also, can you explain the same sensor noise covariance invoice for Hall effects based curve? I think what I explained previously, I think that also hold good here. It's better to have two algos run parallelly so that you can always do the trial and errors in these values. I think that's actually a good way to do that, because instead of starting from the scratch, you can have a base system which is a CC based SOC, and you can do the same exercise here. Okay, I'm moving on to second.
Yeah, Srinivas, you can. I'll take the last question.
Yeah, it's better.
Okay. Yeah. I want to understand what in the battery creates a delay in real physics model, like what happens that creates some capacitance. Apologies for unclear question. A real physics model that happen, that like what happens? Not able to clearly understand your question. Maybe you could rephrase, or you could shoot an email. We can revert back to you.
I believe
Sorry.
Yashwanth, he was referring to a previous, when I think to the response in the previous question, but
Oh yeah. Harit, from where are we getting the C component of the battery? Right? I want to understand.
But I guess if it's,
So
I do
yeah,
understand.
the question
Yes, please.
is that in the real physics, what causes the delay is the electrochemical process that happens in the lithium-ion cell. Which varies, and the response of the cell varies with respect to subject to time. I think that's what causes the real physics creates. Delay in the real physics model. I guess that's what he's referring to. But yeah, I think what is essential here to understand is that each components R, C, whatever we derive, it holds good at a particular, as I said, at a particular point of time. What is the age of the battery? What is the temperature at which we have derived those? What is the SOC that we are looking at? So it's a function of a lot of things. So yeah, I think the real physics model, you would need to consider a lot of things like this before you would arrive at actual understanding of how the capacitance varies with respect to a lot of these factors. I think that clears your question.
So actually, I think okay. So I think he is thinking like what creates a resistance or a capacitance. That means capacitance elements in the equivalent circuit we used for the
Yes.
cell, right?
Okay.
So I think it's better to take like this is not like there is a resistance or a capacitance that present in the cell. So, but the behavior of the lithium cell, we can recreate that behavior using this type of electrical circuit. That's what actually each because there is a universal law like you can create an electrical equivalent circuit to any system if it is able to it is based on a physical system. So
Right.
here it's not like there is a resistance or a capacitance present in the cell, but using a R RC combinations, you can create that type of signal which actually the cell is behaving when you do a C rate charge at the cell. It's not like there is a resistance or a capacitance present in the cell. It is just like
Right.
we are modeling the behavior. So to get such a behavior, we need these RC values. Which are again we are calculating from the cell behavior itself, which is a HPPC test. Okay, it's not like there is a resistance or capacitance present. It's just like representing that behavior using a RC network. That's it. So okay, there is no relation between the cell internal chemical or its RC values that is.
Right. Yeah,
Yeah.
thank you, Srinivas, for that. Yeah, I think Samisha, we have reached the end of it and also overshot by a lot.
Yes, thank you, Yashwanth, and thank you, Srinivas. Thank you, Kathy, for hosting us. And it was really nice having a session with the Formula Bharat.
Yes, thank you so much. I really appreciate both Yashwant, Srinivas for your time. Samisha, thank you again for getting back to